So it's, when you're making examples for class, you can either do something that's instructive but useless, or useful but so complicated that it's worthless pedagogically. So we picked the first book, totally useless application, but it shows some of the important features of the protocol. The totally useless application is you have a client that's doing a network query, it gives back one line for its query that's the load average of the server. So you're finding out about the load assumption, basically get a string. So you ask a question, you get the string back. Let's start by looking at that in IP. Figure out where my cursor is. And we're doing this in Python just because it's nice compact code and fits on the screen. So this is the client side of that, the guy that's asking the question. So down here he's going to ask the questions, just send a question mark to the server, get the answer back, and then print out what he got. There's some stuff you got to set up. You got to go import the socket library. In IP, you've got to identify the server, the machine that you're going to talk to. So it's 127.1, which is this machine, the local host. And then the service that you're going to talk to. And so I picked a random port name, 54321, and say that's my load average service. So I'm going to do it 10 times, make a socket. There's an internet socket, and I want to talk over a TCP stream. And then I've got to connect to that service. So that's what this tuple is about. How we name a service that is the port that is listening on. Send in my question, get his answer, print it out. Then I close that socket and do that 10 times. If I fire this off, immediately dies because there's no server list. Let's make a server list. Okay, here's the server side. Go get socket. We're sending back a date for some useful logging information and the system load average, so we need to import the system, the OS interface to get the load average, date time to get the date and time. This is the line that we're going to return, so this routine is common to all the examples. It's just a response format. The server-side model is pretty similar, except you can put a wildcard in the host. You can say, I'm willing to listen to any client, as opposed to I'm willing to listen to any client on the same host. So the way that you express that in Python is you put a null string into the host, you have to put your service, you make a socket, and then you have to tell the kernel that you're listening on that socket. Your service is available on that socket. That's what this bind call is about. Then you listen for requests. You say, allow one outstanding request. Then you sit in a loop, give you a new request. You pull out his data. If he sent you anything, then you send it an answer, which is like a line. And then you close the connection. TCP's stream-oriented, so it's really hard to handle multiple queries from multiple hosts without doing a datagram-style protocol, a message-style protocol. So this one was set up to take a single answer for TCP connection, and then if somebody wants another answer to the TCP connection, that keeps this well from getting really complicated and rigid. running into multiple hosts, each sending you multiple questions that were being asked of you. So start off with server.
Yeah, that's page. Yeah.
Okay, so these are the answers that we got from that server. This is the time when you generated it. What that parameter is.
Process of the
PID.
yeah,
And we iterated it 10 times, and the difference between these timestamps gives you an idea of how quick it's going. Took a lot of 2 milliseconds for that one, 300 microseconds for that one, 500 microseconds for that one. So it's cranking along pretty quickly. Small number of milliseconds to microseconds. So the equivalent of the client in CCN for Python, some imports to get the base libraries that we need. This is a lot like the socket call. This is giving an handle back from CCN. So this is the communication context so that you can talk to CCND. Because the work in CCN doesn't live entirely in the kernel, a lot of it lives in the library. This handle has more state in it than just what's in a socket, which is a file descriptor, because all the state is in the kernel, which is exactly. And then we need, rather than a host and a service name, we need the name of the data. So we pick some weird line makers, the name of the data. So you're asking for something that starts with a prefix line maker, and we're going to go around 20 times asking, on this handle we want to do a get, so this is issuing an interest in / line maker data, and we'll wait forever for an answer. That's a timeout millisecond minus 1. What we get back from the get, if it doesn't time out, we can't time out, is a content object. When we get back a content object, we get the current date time. We're going to print out the time, the name that we got in the content object, and the content that we got in the content object. So time, the name of from the answer, and the data from the answer. So you can see the size are about the same size, right, for similar problems, not like wildly more complicated. A little bit easier in the naming.
Slide that window just a little bit further right because this sector is like
This started actually using CCNx do that in its bin directory. There's a CCNx start. And if you're working on the homework, you might want to do this part, which turns on interest data debugging. So you get log entries for each interest, log entries for each content object, or syntax for each data packet. The default debugging gives you a very minimal level of logging. So it was a CCND running, so CCND start closes down anyone who's currently running and then starts up a new one. And that's what all of this garbage is about. So at this point we should have a CCND running. So the server side of this is not nearly as small as the client side of it. In imports, there's the response that we're going to return. Here's the name that we're going to be generating our response in. Normal startup, you have to get a handle so that you can speak to CCND. Because you're generating content, you've got to sign content, which means you've got to have a security key, public-private key pair to sign content. So when you build the distribution, it will create a key for your machine. You stick it in your home directory. This will pull out that default key. When an application-specific one, we'll put it here. But we're using that CCND handle. Indexes method to get the default key for this machine, where you need to have both the key and the key locator so that the client can validate it. And the key locator goes in the part called the signed info. The key can be inline or not, but the locator can say the key is inline in this packet. I think that's what we're going to do with it. Jim, pretty sure this is your,
Yeah.
it's got comments in it.
No, I definitely rather than think about the question you're asking.
So this is the setup part. Then you need a routine that's going to generate the response. And that's what this piece is going to be. So this routine will get called when an interest comes in. It can be an interest that says we're going away, which is the final. Do nothing. You can say that I've got an interest packet that you should respond to. So what it's going to do is pull the name out of that interest packet, pull the payload, and then make the packet called a content object to return. So content object's got a name, data, and a key. It's a triple, 3 things. So it gives you the context of the information, the name of the information itself, and then the provenance of the information. You think of it in terms of answering a question, there's 3 things that you've got to supply. You've got to supply the answer. If you're working over broadcast media, many different parties could be answering different questions over that media. So you've got to say what question you're answering, just the reply. Somebody says, what time is it? Somebody else out 32. You don't know if they're answering the time question. Probably not, because 32 is not a reasonable time. So you have to include a name to give you context for the question, and then in order to be able to construct a robust security model, you've got to know who is saying that this answer is an answer for that question. You've got to have what's called provenance information. That's what the key gives you. So a CCN packet includes those 3 things. There's a formal proof that was originally done by Ron Rivas, showing that if you have those 3 pieces of information, name, data, and provenance, you can construct pretty much any trust or security framework that we know how to construct. Anyone that's formalizable. Those three are necessary and sufficient. They're not unique. There are other ways to construct trusted systems, but this is one way, and you can't remove any one of those three, three in order to get a decent trust model. Big digression about keys. So we're going to make up content objects that have the payload, which is that line that we got back on maker. Then we have to give information about the key, and that goes into something called signed info. So we make a signed info, we stick the key identifier in as the publisher. We say what kind of type packet this is. It's just something that's got data in it. We put in the key locator, grab way up at the top, and then we stick all the signed info into the packet. Once we built the three parts of the packet, we can sign it, and we sign it with the key that we got, the default key that we got. Now we've built a packet that we believe matches this interest. So we do a final check to see if the content object matches the interest that we've got. And we know it matches the name because the only interest we would accept are our name, the line maker name. But there are some other things that can go in the interest. Exclude filters and publisher restrictions. So until you built it, you're not sure that you can actually answer it. That's what this is about. Check to make sure that the packet that you've got actually answers the interest, including all of its fields. And if it does, then you put it on the handle. So this is sending data back to the consumer. If you didn't get any errors, you can put it in a print so you can see that this server actually generated the message. Then it returns to the run loop to call it saying it consumed the interest. It's not done with that interest. If it got an error, then it's going to put out an error message. So I can do it. And so that's handling each interest packet. Here's the top of the server where we're sending that up. So we take that routine, we get a pointer to that routine, and we're setting it, we're associating this routine with the name that we're listening for, the line maker handler. So this is binding that name to the procedure that's going to handle it. Then we go into a run loop. This is just going to run forever. Basic server.
There's the language model or a library model architecture that I want to point out about this with the run loop. And that is, first of all, who remembers, we're in Python, right? But who remembers what library that means that we're mostly using? Anybody? Anybody remember what I said about what the Python bindings are on top of? C library, that's right. So an important thing about the way that the C library is organized is it is organized. Thank you. It is organized as a single threaded event loop model. And you see that here in the Python code because the Python code inherits the same model of the underlying C library. That's not the same as the Java library. It's an important thing about how the C library works.
Yes, people that did Java had drunk this horrible thread Kool-Aid. So Java thinks that we should do everything by making a zillion threads. And then if you profile it, you find that it's using 99% of its time in locking. This is, Python is following the C model, which was designed to be pretty low-level matching new processors and pretty efficient. So we run that guy, down in the CCND, our logging spit out a whole bunch of garbage, incomprehensible garbage. What this is about is when you've got a process that's listening for interest, it's got to tell CCND that it wants those particular interests. And it does that by sending a specially formatted interest to the CCND, where embedded in the specially formatted interest is the thing that is listening for. So what we've seen going into CCND here, these log entries are the hex representation of this magic interest. Is called a register. It's the way that a process says, give me interests that match /line maker. Saying that to the local CCND. Many processes can say that. You can have multiple consumers, multiple listeners of interest, multiple producers of data. Each one's going to go to his local CCND and say, give me data that matches this interest. And since we turned on detail logging, what you're seeing is that registration, which is a binary protocol between the apps and CCND. Just runs on the local machine. That's caused our server to start running. Now if I go back over here, and fire off our reader, see a similar thing to what I saw on the IP side. Line maker, PIDs, load averages, and especially the timestamp. But if you look at it for a second, you might notice that all those timestamps are the same. This is the time that it was received, and this is the name out of the content object. This is the content of the content object. Any guesses? This isn't right. In the IP case, the times changed because they represent the time at which the response was generated. And this says that CCN can generate responses instantaneously. And I know that's not true. It's not that quick. So remember that we're going to CCND with this question. You're asking for a /line maker object. It's going to return any object that it has that matches that question. Well, after the server generated one, and we were printing out every time it generated a line, which it had to print, generated one, it put it into CCND. That answered the question that this reader asked. And the reader asks the same question again. Well, the same object answers that question. If it answered it the first time, it will answer it the second time. So CCND happily gave it back, and if you keep asking forever, it's going to keep giving that same object back. This is the big difference between an information model and a conversational model. Now, it's a difference sort of less in the wire than in all of the mechanism that's hidden for us, from us. So if you look, I need to find my cursor, there it is. Here's a TCP/IP packet encapsulated for Ethernet. So Ethernet header, IP header going up to there, and then TCP header going up to there. When we wrote that first client and server, we've got the kernel that's building all of this packet. Routing inside the kernel is building this part of it. We supply enough information to get the IP source and destination addresses and ports. So those bind and listen and connect calls were letting us build this, and TCP is filling in the sequence numbers and the acts. This is all stuff that's kind of happening under the covers. And we think of, now network protocols, and oh yeah, there are all of these headers, and I write the protocol implementation, and it's responsible for filling in these headers. In the information networking, there are no headers. There's names and data. That's all you've got is names and data. And you can't put this information in the data because the data is the payload, is the stuff bits that you're trying to move across. So the equivalent of this information needs to go in the name. In the TCP case, a packet tells you where it is in the original user data stream. That's what the sequence number is. It says 9 bytes, 15 through 100 of the data stream. That's the name of the packet, which at the TCP level is used to reconstruct a continuous data stream. If we want to get, oh, and we get the next packet by sending back an ACK that says, I've got packets up through 100, now sending 101. So if you look at the TCP data stream going across the wire, the ACK stream is the client saying what it wants to get next. And the data stream is the server saying, okay, here's piece 50, here's piece 200, here's piece 600. You're getting back name chunks of data, but we're not used to thinking of these things as names. We're used to thinking of them as protocol headers. But what they are is names that give context to the information. In the case of TCP, the information in the context of a conversation going on between two machines. But the thing that made that first example using the internet work was the fact that we've got this name for the different pieces, and we've got this sequence number, or this ACK number, where the client can say, okay, I got that one, I need a different. The way to get different pieces of data is to somehow reproduce this function. The client needs to be able to say, okay, I've got your first packet, give me a different packet. Give me something that I didn't have. Easiest way to do that is to sequence things, is to tack on a number so when the client gets number 5, it can say, okay, give me 6. Here's that change. Pretty much the same code as before. We're going to start out by asking for this line maker data item. This is identical to what we were doing last time. But giving, this is the reader side, yes. Big difference is in the name we get back, we're going to make the line maker guy put on a sequence number so we can tell his responses apart. And we're going to make it a sequence number, something that increments by 1. So as soon as we get a response, we know what the next response is. We're able, because in order to not get the same data again and again and again, we've got to make sure that our question is different from the last question. We also have to make sure that it's a question that the line maker will receive and be able to answer. So, stick on a sequence number. This check says if the name we get back has more than one component, then the second component is going to be a sequence number. So, split it up into components. For the last component, turn it into an int, increment it, turn it back into a string, put it back in the name. So, say the last component is a sequence number. I'm going to take the last sequence number I've got, bump it up by 1, and then I'm going to use that as my new name so that I'll ask for the next in sequence. So this is exactly what TCP is doing when it generates ACKs. Right? You get an answer, you get a data packet from the other side, it's got a sequence number in it. You take that sequence number of the last byte in the packet, you put that in your ACK field, so you're essentially asking the sender to send you stuff beyond that sequence number, because you've got the same pattern, exactly the same model to solicit new data. First thing I'm going to do is run this. And it failed. It didn't work. And this pattern is, I don't know what sequence number the server side is using. So I'm going to ask for anything from LineMaker the first time to try and find out what his initial sequence number is. And after that, I'm going to use it. But I still got all this LineMaker junk from the previous example that's sitting in CCNd. And so if I just run this rewritten client, it's going to pull the old stuff out of CCNd, which didn't have a sequence number on it. So before I can run this new example, I've got to restart CCNd to get rid of all of the stuff that's hanging around with it. And I point this out because if you're working on the homework tonight, you're guaranteed to be burned by this. Data persists forever. That's a fact of life today. And this NDN architecture makes that really obvious. All of your mistakes persist forever. So while you're debugging and you think you fixed something and you code up a new server code and you run it and the client fails, there's the old chunk. All of your mistakes are still sitting inside of the CCNd, so make sure that you restart it.
Now, just one small follow-up point about that. In this case, we're going to restart the CCNd, and it's the only CCNd in our universe. It's not talking to anybody else. It's just the one thing on this machine. And we're doing this for the convenience. But of course, when you think later about real applications, they're going to be dealing with a real world in which there's other data out there, and you can't simply say, let me reboot the entire world. So in general, applications have to think about how to ask the questions to get the data they want, realizing that there might be things out there that they didn't expect. And for simplicity at this stage, we're not going into any of the issue of how you do that. But it is an issue.
So fired off that new reader guide. We look over here at our CCNd logs. So by default, interests get timed out after a while. So that's, here we see the interest coming in, is asking for this LineMaker. The interest times out, it expires, and the library automatically regenerates it because we set the application level cannot be infinite. So we're just going to see the app issuing that interest, CCNd timing it out, reissuing that interest. It's going to sit there forever waiting for an answer. So now, here's the equivalent server. The server is essentially identical to the previous one because the incoming interest that it gets has got a sequence number on it, and it's responding to that interest. It's got to use the same name, so we don't actually need to do anything different. We just send back our response using the interest that we got. The only difference in the producer is right here, where that first interest that's sent is the one where the client is trying to figure out what the sequence number is. And so if we get a name that doesn't include a sequence number, we generate a random sequence number and stick it on the name. So that's our initial sequence number. Pick some random one. Other than that, we'll just use the name the client gave us because it's got the next sequence number and we'll respond to it. So it's pretty much identical code to the previous example, except for tacking that random sequence number on the initial unadorned interest. So this time we get different responses. This is the name, so we can see the sequence number increment. We can go over here and we can see that the server answered 10 different questions rather than one question, the rest coming out of the cache. So all of the pieces are so the takeaway that we want you to get from this is that if you move to an information-centric architecture, the names have to say everything that you need to say. Most of what you do in this architecture is name engineering. It's designing a set of names that cause the right communication to happen. And it's really easy to screw yourself up by missing information like sequencing or temporal versioning. Because the properties of the information evolves over time and has to be busted into pieces, so you have to take it apart and put it back together again. All of those things, you have to have fields inside the names that let you do those things. They're there in the IP packets, you're just not used to seeing them. Because IP is presenting you this very high level of stream abstraction. But underneath, it's busting things into pieces, putting sequence numbers on them. It's unfortunately not helping you with temporal evolution because it doesn't know about context in terms of conversations which are important. But there are these things that it's doing for you, that it's always been doing for you, that you have to do for yourself as you move to this architecture. So there's library routines to help you is really common. So there's library routines for segmented objects, there are library routines for versioned objects. We're going to get into that a little bit later. But we wanted to give you some understanding of why those routines existed, what problem they're solving. And the problem that they're solving is I'm trying to pull information out of that server, I'm trying to pull load averages, which are changing over time. And I don't want to get the same answer again and again and again out of the cache. I want to get new answers. And the way to get new answers is to ask a new question, which means I have to change the name. At this point, we wanted to
Actually, a few seconds.
yes, go for it.
Are there, first of all, are there questions over there? Thank you.
The question is, can the customer get a list of the producer's content? Actually, because I see the CCNx protocol said that it will keep only the one content, the first content, or some content filtered by the interest. But anyway, the given content should be decided by the interest. So actually, but sometimes I don't know what exactly I want. So
yes.
I'm asking, what do you have first? And then after the list, I can decide what I can get.
So that was essentially that was this part of the code. This is saying, I don't know what your sequence number is, so our agreement is that you're giving me sequenced packets.
Yeah, but actually sometimes I don't know what exact sequence number I want.
So this particular pattern is, so you could be asking two different questions, and one of them wouldn't make sense. So, all network communication, all communication requires shared conventions. Right? We can talk because we share a language. I'm American, so I don't speak enough languages, but we at least have one in common so that we can talk. Two IP nodes, two TCP nodes can speak because they share all of the IP and the TCP conventions. When you're making a client and a server, you're or you're making a set of information to be consumed, you need naming conventions that are known by the clients and by the server so that they can interpret the information. A naming convention here is, this is sequenced information, that every new piece of information has a new sequence number. Sequence numbers are dense, they increment by one, so that if the client gets one piece of information, it knows all future pieces of information, and that's coming just from the conventions. It's very much like the TCP sequence number conventions. So you need a mechanism so that you can find the first number. You find a number that the producer is currently using, and given that, then you can extract the rest of the information. So that's this convention. This convention is really similar to the way that a server rendezvous with a client in TCP. When you've got a web server, it doesn't know who's going to talk to it. So it's sitting there listening for anybody that might want to talk to it. The first packet comes in, the web server says, now I have the client source address, because that was in the IP packet, and I've got his port, which is now unique, and now the combination of my source address and service port and his source address and a randomly chosen port give a unique identifier for this conversation. And he sent me a TCP SYN packet, so I know his starting sequence number because it was in his SYN packet. My answer will give back to him my starting sequence number. So there's this very elegant and largely undocumented rendezvous between clients. So the core problem that you face in these protocols is most of the protocols are unidirectional. IP packets go one way. And you need to bootstrap from unidirectional to bidirectional in order to have a conversation. And you need to do it in a way that doesn't require all of the parties to pre-set up a communication to know about one another in advance. And so the IP pattern is the second host. The initiator knows the service. The thing that is initiating to the server side gets all the information that it needs in the first packet. And the naming convention is it can take the addresses and flip them around, and that's the reverse direction. So the first packet both gives the starting segmentation information and it gives the reverse channel information. And those are all just name transformations. Right? You're taking this long name with host addresses and ports and sequence numbers and MAC numbers, and you're flipping all those numbers around and sending them back the other way. And all that is taking a structured name and doing some simple transformation that gives everybody the same starting point and then they can communicate. So we've done a partially qualified name, knowing that everything the server is going to generate has got a sequence number in it. So any answer that we get for this is going to have a sequence number, and since it's a sequence number, I can just keep asking for the next one. So that's sort of following the IP pattern and the general theme of we need shared conventions, simple shared conventions in order to communicate. A thing that people have many times tried to do and fail is to sort of build up the conventions on the fly. So this was done with a lot of RPC protocols where you would make queries to say, well, what exactly can you do? Tell me the routines that you support. And then for each of these routines, tell me what the parameters are. For each of these parameters, tell me what its format is and what its encoding is. And you would try to write servers in those protocols, and they chug for about half an hour and do nothing while they were just trying to figure out what the other side did. And it's, you end up with this problem that's sort of Turing complete, that you can never find out enough about the other guy in order to successfully communicate with him. Because in the end, you need to know the semantics of the information in addition to the syntax of the information, how it's laid out. And that's not communicated. That's not something that you can ever say. So what we're doing here is following the basic protocol pattern of trying to fill in information that's known to one side but not known to another so that you can get them both in sync and communicate. But that's the limit to the discovery that we can do. The discovery of the full capabilities of the universe. Figuring out exactly how to talk to this guy when you don't have any shared conventions. We've tried that and it doesn't work.
Now, there are more complicated cases, and we're going, I put a note on the board. Yeah, right, because I want to come back to this because we're going to look at a case this afternoon that deals with a situation where you don't have this, the convention does not embody a predictability of knowing that we have densely packed sequence numbers one after another. So we're going to touch on that, but we have a separate example for it. And so if we can remember this and come back to it, we will fill out more of the answer about that. And I think we will fill out yet more of the answer again at the end of Wednesday when we're going to talk about some of the frontier work that we're doing that's not even, we haven't even begun to touch on. So that was actually very helpful because it covered, I think the answer covered a number of the supplementary points we were intending to make here. But just a couple of things to make sure that you didn't miss it. And I think from part of your question, you didn't miss it. But just want to point out, does everybody remember when we ran the producer program at first, and it has this print to print out when it produces a piece of content, and it just sat there and nothing happened, right? Why was that? What is that telling us? No interest arrived. That's exactly right. No interest, no data. Data doesn't flow unless there's an interest in it. Okay, and that's one of the basic principles. So we see that even in this very simple program. No data, no interest. Now, here's another thing we see. When we had our program go through, and it had in the consumer side, it has this loop, right? There's only so many times that it's going to ask a question. And whether or not, now, in the first instance, we had a program, and it asked the same question over and over again and got exactly the same answer. But each time it asked a question, it got an answer. When we fixed the program and we introduced this sequence number convention, then we had something that still asked a number of questions and got an answer. Now we had a program, that producer is capable of producing an infinite number of answers, right? Anybody have any problem with that? That producer program could produce an infinite number of answers. But when I asked the question, when the consumer asked the question, how many answers did it get? Anybody? This is an easy question. When the producer did in this API, it was the GET call that caused an interest to be generated and handed off to the network. That was one interest packet. How many data packets came back as an answer to that question? One. That's right. So no interest, no data. One interest, one data, unless there isn't any answer at all. And then one interest produces zero data. And I think we also saw that case when Van was running it before there was a server. I think he ran one of those cases. And because of the API level infinite timeout that we set, the library was doing the work of re-expressing this interest as it timed out. And yet, every time it would send that interest again, that's what we mean by re-expressing. It transmits the interest again. And every time it did that, still no data, so no answer. Now, this may seem very obvious, and if you've read the papers and everything, and this seems totally obvious. I apologize for going on this point, and it's good that it seems totally obvious to you. It's not obvious to everyone. We sometimes get questions of the form, well, if I ask this question and send out this interest, will I get like all the movies that match in the world, or forms of a question like that? And it's very important to realize that for flow balance and the stability of the network, where the receiver
is in control and is driving the flow rate. For this reason, one interest gets at most one data, and no data goes anywhere if there isn't an interest for it. So that's one of the other things we wanted to point out. Another one is when this interest was expressed by the consumer, did the data exist? Well, I see some people shaking their heads. How many people say no, the data did not exist when this interest was expressed? Okay, we got a couple people. How many people say yes, the data already existed when this interest was generated? Okay, nobody's willing to sign up for that. So all the rest of you have no idea. Is that you're stuck between these two alternatives, you have no idea. Well, remember that the producer program had this response code, right? The interest came in, and what did it do? It actually produced a piece of content. And in this case, for the totally useless example, as Van said, the piece of content that it produced contains a value which is, or actually multiple values in this case. We've got 3 load average values that are generated at a time, right? So another thing that people sometimes mistake about NDN is that, or that might distinguish it from some other kinds of networking efforts out there, is that when you ask a question, you don't have to ask about something that already exists. Just like you can ask a question of a web server in HTTP, and the web app can dynamically generate you an answer. That's perfectly fine here. That answer, when it gets made, will have a name that should uniquely identify that piece of data that is that answer. But that data didn't have to be pre-computed and stuffed in somewhere like a repository where it's going to sit until you ask the question. It can really happen dynamically on demand. And that means, by the way, though this program doesn't show it, that means that you can have side effects. That means that an interest can come in, and the fact that you received the interest can cause your program to do something that it would not do until it saw that interest. And we're going to see that come back this afternoon as well. So dynamic data generation is just fine. We talked about the memory effect already. We talked about conventions, the producer-consumer agreement. Now another thing that I think we covered, but again, just to quickly make sure that nobody missed it, when that program asked the question with just LineMaker, it got an answer, right? And the answer that it got in the second case, when we had a sequence number, that was the thing that told you where the sequence number sequence started, right? So you can ask a question with only partial information, the prefix of the answer, and you can use the information that comes back in the answer, in the name of the answer, to figure out what question you're going to ask next. I think we pretty much covered that one. Okay, and I think the last thing we wanted to show is, but we have to maybe run both of them and look back in the scroll. We wanted to compare the timestamps from the out of cache before that. That is the receipt timestamps, right?
Yeah. So in the case where we were getting it out of the cache, all these numbers were the same, because it's the same line. Here you can see that they're changing. Both the server and the client are running on the same machine, so these timestamps came from the same clock. This one was put in the message when the server generated it. This one was put on by the client when it printed it out. So the difference between those two numbers is the time it took the message to get from the server to the client. This is the time that the server built it. So this gives us a measure of the processing time and what do we see? So 0.85, 0.88, so 3 milliseconds system. And that's server process. It's got to sign the packet. So we pay the cost of crypto through CCND, back from CCND to the client. So a lot more work than you have to do in the TCP/IP case. I was thinking about it the same amount of time. And this is through Python, which is an interpreter.
And don't gloss too quickly over that. We have to sign the packet. The current CCNx library has very limited options for signing the packet. And these packets are being signed with public key signature operations. And that is relatively time consuming compared to other things. Now, the libraries we have do have some implementation of techniques to amortize the cost of a public key signature over a bunch of packets when you're doing a whole sequence of them. But as you're doing sort of individual one-off things, sometimes that signing cost can be very significant. And one of the things that's an active area of work and exploration in the NDN project is alternative signing algorithms that involve different performance trade-offs for different application scenarios that you might have. So that's something not to gloss over. Yes?
Actually, the point about the sequence or packet name, it was a very small way to do to handle the packet name. But I'm just wondering that what is the way to handle the version, different version?
Great question. I think we can get there later. So if you could defer that one, we should hit it this afternoon. It was on the topics list. We need some more mechanism, I think, before so for the versioning, put on a version number, and we want to put it in the name. Two common problems are segmentation. You've got to take a big name, less than piece, and disassemble it and then reassemble it. And for that, you want some sort of sequence number, some sort of piece identification. The other is content evolves temporally. You have a new version that wants to supersede an old version. Timestamps are a convenient way of handling temporally evolving content. You need to do things that don't require synchronized clocks everywhere because you won't get those. Clock synchronization is a very hard problem. At best, you get approximate times. But the fact that we've got a lot of information, including publisher information, so that we know the party that's generating the timestamps and connecting to the system themselves. But you still need some operations on the client side to say, give me the most recent version. And we need some sort of coherence policy operations on the CCND cache so that the old versions don't sit around and clutter things up. So we've got to introduce 3 or 4 new pieces of mechanism before we can talk about versioning. It's the same pattern, we have something new from names, but we need a couple of those as well.
All right. Other questions?
I wanted to make making this up on the fly since Jim gave you this pitch, Think Different, right? So that was the internet one, and this is the NDN one. And they're not actually that different. Right? It's a really similar pattern. Get a handle, call it a socket, you call it a handle here, and then you somehow associate yourself with the other side. Here it's done by connecting to a hosting port. Here it's done by generating an interest. But the basic pattern of these two is really pretty similar. That has a lot to do with the problem that we want. It's a producer of dynamic information and consumer of dynamic information. There's a lot of stuff that's happening underneath the covers here, like the TCP sequencing and mapping, that's explicit here. So basically what you're seeing happen in this one with the sequence numbers is occupying about 30,000 lines of TCP stack inside the current node here is the sequence and the reassembly and ultimately how it's pushed up to the application. The big difference between these two is this is a much more general model. The only thing that you can name in this model is endpoints. You name hosts and services, processes on those hosts. Those are the only entities that are critical. We could put a host name in here. We could talk to line maker on 127.0.0.1, but we can put much more general names, multiple line makers, multiple clients consuming. That's a single conversation. This is one of potentially many consumers of data, and that server was one of potentially many producers of data. This model includes the IP model, but it's a bigger model. It's any-to-any, and it's focused on the information that's moving around it, as opposed to the conversations that are moving that information. So even though the structures look similar, as we go on through the day, they get more elaborate as we start to exercise more features that are possible in this, but not possible in the other.
My question is still about the run interest runtime package. I think even in TCP/IP stack, when the conversation set up, one side send a few that packet to other side. The other side just response when with the last sequence number it has received. So I think even this conversation is not one to one. Can you say one interest more several
I spent 20 years fixing the problems in the TCP IP strategy. Data packets from one end. So based on that experience, don't do that. Some things that we didn't know when we were designing TCP was how to make a stable network when you have an arbitrary mix of bandwidths, when you have arbitrary node degrees here, arbitrary aggregation, arbitrary disaggregation, arbitrary client population. The phone company figured out that if nothing was arbitrary, if you made everything out of 64 kilobit per second slices, and you clocked everything with the same clock, then you could make a really stable system. Couldn't make it cheap, because to scale it up, you don't get that clock everywhere and working on a really fine rate, but you could make it stable. And a very high-level researcher from Bell Labs was literally screaming at Vinsurf at ICCC, the big communications conference in '78, saying that there was no way that he could ever make this TCP thing work because he hadn't fixed the bandwidth, he hadn't fixed the distribution architecture, he wasn't controlling anything. And when we built the NSFNet, it turned out he was right for a few months that it probably fell over. But it was because the TCP Act policy wasn't well enough specified. In particular, there's a property that a guy named Frank Kelly at Cambridge University showed in 1978 is essential for making a stable system with all of the degrees of variation the internet has. And that's that the system run in flow values. At every point in the system, the packets going into a node equal the packets coming out of a node. And if you don't do that, then you can get arbitrary imbalance, arbitrary delays, lots of queue overflows. The TCP flow balance, because of this ACT strategy, is all the way end-to-end around the sender, through the network, the receiver, back loop. And within that loop, it can be arbitrarily out of that loop. So you can have traffic that concentrates right up to the TCP window size from one connection. So all of the data that's subtracted can end up at one point. And then, since there are multiple people that are using it in different directions, what you get is the multiplier multiplexing level times the per conversation data in transit, which is that you've been following Jim Getty's buffer growth work. What we're seeing right now in the network is something that everybody's been calling congestion, but it's not congestion. It's just massively oversized buffers, which are causing huge delays at almost every point in the network. And those are a direct result of this very poor app policy. If you make it one data packet results in one act, then you've got TCP running in much better flow balance. All the timers start to work better. You end up getting less congestion in the network. You get more information in the act stream, so that you get to a lot of single algorithms. You can't do as well as NDN does because the relationship in TCP is between the sender node and the receiver node, and the network intermediaries are invisible. The relationship, the flow balance relationship in NDN is always between adjacent hoops, so it's between the NAP and the CCND and the next CCND upstream. And so it ends up balanced across every link, as opposed to TCP, which is balanced across the entire path, like the network unbalanced. So this will do way better than TCP with no performance hit. It fixes that indolent problem. The theoretical underpinnings are Frank Kelly's work on the stability of flow balances in a book called Reversibility is Frank has put it as out of print, but he put it on his website as a PDF if you're interested. There's been some additional work, but it's not as much.
Yeah, the NDN website has a pointer for that, so.
But multiple packets per interest really bad. If you want to make an internet, if you want to do something on private wire, do whatever you want. But if you want something that can scale up to the size of the internet, you really have to think about stability, because we've done the experiment of not thinking about stability and having a net collapse to fix it. And we only know of one way to make an extremely heterogeneous net stable, which is to force it to run. Might come up with other ways. There's no proof that that's the only way to do it, but it's the only way that we found.
Okay, and that brings us to lunch, which I imagine you were on thankful for.
So what we'll probably do when we first come back is a little bit of a digression to sort of look at what the same programs look like directly in C and in Java, to just do a little bit of skimming of sort of API differences in those, and then move on to some additional examples. So my understanding is that we have 1 hour allocated. Do you have any announcements or other instructions?